now broadcast this into the world. Okay. So, yes. Thanks for choosing operational research. It's a fancy subject. Any financial math students? Oh, you didn't have a choice, so no thank you to you. But I appreciate your hearing. You still could have stayed at home. Okay. So this is a funny room because this is the business school, so they don't really do any teaching or anything. They just sit around tables and chat. Yeah, so it's not very well designed for learning stuff like maths, but we'll have to put up with that. Well, it's not as bad as it could be. Are you all okay with the setup of these tables? Like this, so you have to be twisted like that. Kind of, yeah. But then you can check with your neighbours what they're doing.
Adjust it if you want.
Yeah, we could adjust it if I want, but if you want.
Yeah.
If you feel it's not working, then tell me next week and we can rearrange the tables in a more workable way. I have to show you this. Do you know what to do if there's an alarm? Run away. Okay? Just don't leave any of your belongings, what's it called, personal belongings. Of course they're personal because they belong to you personally. In personal belongings you don't have to say. So any of your stuff, don't leave it here. Just pack everything and go slowly, no running, peacefully. There's a staircase right here on the left, downstairs, and then leave and then stay there. Any questions about this? Hope not. Okay, so okay, if anybody needs a ring binder, I still have some ring binders, so if you want, does anybody need a ring binder? Because I will be giving out a lot of stuff as usual. So I'll bring some into the lab on Friday, okay? And you can get one of me on Friday. Is the lab on Friday? No, Thursday. Thursday, 12 o'clock, is that correct? Yeah, no. So on Thursday, I'll bring them. That's what it's in here. So if you could take one sheet of this and 2 sheets of this, I'll put it like this. Please.
Oh, wait, silly sausage.
There are 2 different pages on this. And also, before I forget, can you please all sign in? Because now there's a new fancy way with beeping the card in, but it only applies to first-year students and international students who need visa or something. Okay, so let's start now. This is me. This is where my office is, and this is when I'm always there. And if you want something outside of these hours, then just email me and we can arrange a different time. Presumably Philip has told you all this about the assessment in ORFM. So what I'm going to be giving you is similar to last year in decision maths exercises. Now, the point of these exercises is you're not doing them for me, really, because I don't care. No, I do care. I want you to learn stuff, so you're doing them for me. But more than that, you're doing them for yourselves, because you want to learn something. And also, these questions have a slight tendency to reappear on the exam sometimes. Just as a hint. Okay? And then there are assignments. And I'm not sure whether there are 10 or 9, because Philip, I think, only gives out 4. But I'm doing 5. And similar to last year, there is the first deadline before Christmas, I believe, And then there's a second deadline at the end of term. No, it's not term 2. At the end of the 24th week of teaching. For these assignments. Oh no, is it? Yeah. So sometime towards the end of the year, there's a second deadline. It's on the sheet that I've given you out. So on the look at this one. I give you the schedule of everything. Right, when you turn the page, there are the 2 deadlines for submission of these assignments. So the first 3 of my assignments, term 1, and the rest. Okay. And then there's a financial thing test, but the financial part only starts after Christmas. Okay. Any questions about this at all? All good? Excellent. Here. So what we all are going to be doing is we have 2 big topics, and it's not a lot. And the first one is linear programming. And I know we did quite a lot of linear programming in year 1. But what we'll be doing here is looking at some more advanced aspects of linear programming. We did a little bit of duality in decision maths, if you remember. If not, I'll remind you today. So we'll do a bit more of duality, these bits. And then the second thing is called post-optimality analysis. And post-optimality analysis basically is about trying to get more information from the Simplex tableau than just the optimal solution. Okay, so for example, things that we had in the labs as examples, I believe, were how is the optimal solution going to change if I change the right-hand side by a little bit? Okay, do you remember anything like that? So all these things, how is the optimal solution going to change if the price or cost of something changes just slightly? Which are the important parameters whose change influences the optimal solution a lot? And things like that. So this is what we'll be doing in the first term, trying to analyze the Simplex tableau in more depth than before. And in the second term, we'll be doing integer linear programming, which is just like linear programming, except you want the decision variables to be integers. And this can be useful sometimes when you've got things like, so quite often the integers will be just 0 or 1. So for example, you're deciding whether to put on a coat or not. So the number of coats you're putting on is a decision variable, but it can only be 0 or 1. It doesn't make sense for you to put 0.27 coats on, right? So this is an example of things. And then there are many real-world problems. Actually, almost everything can be formulated as an integer linear programming problem. So we'll be looking at this kind of formulations, as we did in linear programming, but this time this is a different sort of problems. And we'll learn how to solve them using 2 different algorithms. So that's the plan for after Christmas. Okay. Any questions about this? So for now, for the next 6 months or so, no, it's just 3. For the next 3 months, we're doing linear programming in more depth. And to solve linear programming, we often used a method which was called the Simplex method. Yes. Does anybody remember this? Okay, so how does, just as a reminder basically today of stuff from last year in linear programming, let's have a look at this so we all know how we can solve it. So how does it go? What does the Simplex method do? first? Keyword?
Objective first.
Objective first. What with the objective?
To maximize profit, for instance.
Well, not sure whether you mean to maximize profit. Yes, the whole point is to maximize the thing, but what do we do? Okay, so keyword slack variables. Does that ring a bell? What are slack variables? Just variables that denote the slack. Okay, so what we do is with these less than or equal constraints, we add a variable there to make the less than or equal into an equal sign. Okay, so what we would do here is write it as 3x1 plus 2x2 plus, we call them S1 equals 160. Okay, and with this one, what we did was x1 plus 4x2 plus s2 equals 200. And then with this one, what we did was half x1 plus half x2 plus s3 equals 31. And now, instead of just x1, x2 greater than or equal to 0, we also want s1, s2, s3 greater than or equal to 0. Is that large enough? Can everybody read it all right? Yeah. If not, I can make it larger. And with the objective, what we usually did was we said z minus 15x1 minus 20x2 equals 0, which expresses that z, which is going to be the objective, equals 15x1 plus 20x2. Right? And we're trying to maximize z. Everybody okay with that? Should be just a reminder. Okay, so what did we do next when we were solving this? We used a table like that, didn't we? So what is the basis?
X1, X2, Z.
S1, S2, S3, X1, X2, Z. So who is for X1, X2, Z? Just one person. Who's for S1, S2, S3? So it wins? Okay. Democracy. You can always overrule democracy if I want to. So we have S1, S2, S3. Okay, so this is the basis. So these variables are called the basic variables. This particular basis. What special property does the tableau have with respect to the basis? You know what I mean? Pardon?
Can you repeat that?
What special property does the tableau? So, okay, so first I should say that all the remaining boxes here will have some numbers in them. And there is a special property which we call the simplex property, which the tableau has to have when you know the basis. Do you remember what it is? No? Yes?
What's in the basis?
What's in the basis you put as 1? Like, is that what you said?
Like the first row.
Yes?
One column will have 1.
That's correct. And in the S2, well, Oh, and right. So that's what Alice said. 1, 1, 1.
Yep.
Right?
But when you go down, the rest are zero.
And the rest of the column will be zeros? Okay. Right. So we've got part of the tableau done. Now, what are we doing for the rest of the tableau? What does the val do? What does it take?
Values on the right hand side.
The right-hand side, yes. So we could call this the right-hand side of the val. Now you see the S1, where it's 1, it says 160, so that's what we put there. 160, this one is 200, this one is 31, and this one is 0. Okay, and x1 holds the coefficients of x1 in these equalities. So comes in a slightly different order, but the order doesn't really matter. It shouldn't surprise you that the order doesn't matter. But so we've got 3, 1, 1/2, and -15. We've got 2, 4, half, and -20. Okay, so that's the first tableau. Everybody all right with that? Yeah. Now the important thing, which you should keep in mind, is that each row of this tableau, including actually the objective row, expresses an equation that is satisfied by all the feasible solutions. Okay? So this equation, 3x1 plus 2x2 plus s1 equals 160, is expressed by the first row. So it's 3x1 plus 2x2 plus s1 is equal to 160. Okay? The second equation is x1 plus 4x2 plus s2 equals 200. And the third one, and the objective is the top equation, z minus 15x1 minus 20x2 equals 0. Now, what we could do, but what we don't do, so I'll make it in red, what we don't do, usually, because it's, that you can think of another column being here, which is called z, and which has got 1 here. So you could think of the objective as an additional basic variable. Yeah, so I could call this objective z, because z is the objective. Does that make any sense? Right, so the last equation, the last row, corresponds to the equation which you see here at z minus 15x1 minus 20x2 equals 0. Okay? Now, we don't usually write that column because that column always stays the same. You never want to take z out of the basis, because if you take z out of the basis, you don't know what you're optimizing. So z always stays in the basis, and we don't even say it's a basic variable. We just keep it there somehow independently of the rest of the thing. All right? But if you wanted to, you could write it like that. Okay, so this is the first tableau. We're going in time, right? Oh yeah. So right. So what comes next after the first tableau?
So we choose x2 and find the ratios using the basis and values in x2.
So let me repeat this for our viewers who probably didn't hear it. If I heard it correctly, so you pick x2, and then you want to do what with x2? Insert it into the basis. Is that what you said?
Yeah.
Okay, and then one of the variables has to leave the basis, because the basis always has 3 variables in it. Right? Now discounting the z. The z is separate. So why did you pick x2?
was negative.
Aha. So it has to be negative somewhere. So yeah, right. So you look at the objective. If it's negative, so negative in the objective means there's something wrong. Not really wrong, but there's something that tells you that you have to work. You're not finished working yet, okay? It's an important thing. Just remember this. We'll come to this in a second. Okay, so the negative number, you look at all the negative numbers, you pick one of them. For example, the one that's largest in absolute value, so the most negative one. That is a rule of thumb. It's not necessarily always that one, but it has to be negative in any case. So, right. So x2 will be the variable about which we say that it enters the basis. And then you said something about ratios. Does that ring a bell? Ratios. So what ratios are we doing? 160 divided by 2. Okay, so the ratios, I'll just write them here. It's 80 because it's val divided by the x2 column. And here it's 50. And here it's 62. And here it's minus 20. Oh no, we're not doing that. Oh no, it would be 0. But we're not doing that. Sorry. I'll stop. Okay. And now we've got the ratios. What do we do? S2. Why is that? How did you?
This is the smallest ratio.
The smallest ratio? Oh, right. Yes, that's correct. So the least ratio is 50 here. So that means that now in the next bases that we've moved to, there will be x2 here, and s1 and s3 stay where they are. Okay, now by means of row reductions, what we have to achieve is the simplex property again. So you remember the simplex property was we have the 1 and the 0. We have the 1 and the 0, or the 1 and the zeros. So now x2 is in the basis. So what we want is to have the 1 and the zeros like this. Okay? And what are the row reductions?
Divide everything in the S2 that was in the S2 by 4.
Yes, that's one way of doing it. So yeah, so this, because there's a 4, I want a 1, I just divide this by 4, and I get 50, 1/4, 0, 1/4, and 0. Is that right? And then by subtracting a suitable multiple of that row from all these 3 rows, we get the zeros over there. So I need to take away twice this. So twice these numbers, 50, and so on, from the first row. So I get 160 minus 100 is 60. I get 3 minus 1/2 is 5/2. Is it? I get 2 minus 2 is 0, which is good. I get 1 minus 0 is 1, which is good. I get 0 minus 2/4, so that's minus 1/2. And I get 0 minus 0, which is 0. You still with me? And I need half of this new row taken away from the second row. So 31 take away 25 is 6. 1/2 minus 1/8. That's 4/8 minus 1/8. So that's 3/8. Is that right? I don't know. Doesn't really matter. There should be a 0 here. There should be a minus 1/8 here, and a 1 there. Hope I'm doing it right. It's about to bring the actual solution. More probably correct. And now here, what we're doing is adding 20 times the new x2 row. Yes or no? Okay, so 20 times 50 is 1,000, plus 0 is 1,000. 20 times 1/4 is 5, minus 15 is minus 10. 0 added to 0 is still nothing. What did I say it was? 20 times, so that's 5. So is this 5? And this is 0.
So why is x1 minus 10?
Why is x1 minus 10?
Oh yeah, it's
Is it because I've taken 20 times 1/4 is 5 and added it to minus 15? Okay, so is everybody clear? So what's this whole process called?
Pivoting.
Called pivoting, or a pivot step. So once we go from one basis to another basis, that's a pivot step. And the whole process, when we're doing many pivot steps, is called pivoting. Everybody happy with that? So what will we do next here? X1 into the basis. I'm not going to do that because now everybody knows what we would do. However, the question is, when do we stop?
When there is no more negative value in the objective.
Okay, so pivoting stops. When the objective row contains no more negative numbers. Okay? And then the tableau is called optimal. Okay? So that shouldn't come as a surprise. The caveat for minimization problems we want no positive in objective row. Okay? And then, in this case, something that we call the basic feasible solution. Do you remember what the basic feasible solution was? Anyone? It's very funny because there's someone right there through the door who waves her hand like this, and sometimes it looks like, yeah, I know the answer. I want to tell you, but it's actually behind two doors. So the basic feasible solution corresponding to the current basis is an optimal. Okay, so when I go back to the tableau that you can see at the top of the screen, what is the basic feasible solution here, corresponding to the basis S1, X2, and S3? Get it? It's always the same people saying something and the rest of them, but it's always like that. Okay, so the basic feasible solution here is, what is X1 when you look at this tableau?
0, 0, 0.
Yes. X2? Yes. S1? S2? S3?
6.
And Z? Yeah. Okay, so now you know what the basic feasible solution is on the basis. Okay. And this is not the optimal solution because this is still not optimal, but it's a feasible solution. Now, what does the word feasible mean? What is a feasible solution?
Possible solution.
In what sense possible? Well, in the sense that it satisfies all the constraints that we started with. Okay, so when I'm going to move it away now. So when you look at all these linear inequalities, and you plug in x1 is 0 and x2 is 50, they will all satisfy all these constraints. Or when you take all the slack variables, x1, x2, as they were, s1 is 60, and so on, and you substitute into the system with slack variables, they will satisfy all this. And that's called a feasible solution. But also they will satisfy non-negativity. Okay? So the non-negativity is kind of important here. And this is what tells you that a certain basis or a certain tableau is feasible. So a Simplex tableau is feasible if all the entries in the val column are non-negative. The objective row doesn't have to be, but all these 60, 56, as they are, have to be greater than or equal to 0. Okay, and then we say that the tableau is feasible. Now, last year, what we were doing in decision maths is we never encountered an infeasible tableau unless you made an error. So if there was anything negative in the val column, we said that's just wrong, not possible, not allowed, go back and do it right. However, this year we will allow it, and that's a step forward. Okay. But we'll have to do something about it, because obviously negatives in the final solution that we want in the optimal solution are still not allowed. So what we're going to say is that the goal of pivoting is to find a tableau which is both feasible in this sense and optimal. Okay, so feasible means no negative values in the val, and optimal means no negative values in the object. Any questions? No. You have to ask a question, because otherwise you'll fall asleep. Who's already fallen asleep? That's not possible. Educational theory says that after 20 minutes you fall asleep in a lecture. It's unavoidable. It's already been 35 minutes. Something's wrong in educational theory. Okay, so what we'll be doing, what we'll do, instead of writing, well, not always, but for the theoretical considerations, it's nice if we can rewrite the tableau in a different form. I'll show you. So you remember this tableau expresses some sort of equations, right? And you can write these equations in a matrix format. So 160, 231 equals 3, 2, 1, 1, 4, 0, 1/2. No, what am I doing? This is wrong. It's not all wrong. Again, 160, 231 equals 3, 2, 1, 4, 1/2, 1/2 times x1, x2 plus, and now I'm being too wordy, so the identity matrix, 3 by 3 identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1, times S1, S2, S3. Does that seem plausible? So who still remembers from year 1, linear algebra, how to multiply matrices? No one? That's a very sad result. Come on. Does anybody remember how to multiply matrices? Oh dear. Okay, never mind. It's the first week after holidays. It was always going to be like that. So multiplying matrix times a vector like this means you take 3 and 2, 3x1, 2x2.
Row times row times column, and close row times.
Yeah. So the first row times the first column, and then you add them all up, and what you get is... Okay, just to remind you, in some sense I'm being too nice to you lot, because I should just say, okay, read it up, because you're supposed to know this, but okay. But for the sake of everybody understanding what's going on is, so this is going to be, it has as many rows as the first matrix has rows, and it has as many columns as the second matrix has columns. So it's going to be 3 by 1. Okay, and the first row is, you look at the first row, and you look at the first column, and you do 3x1 plus 2x2. And the second is going to be x1 plus 4x2. and this is half x1 plus half x2. Okay? And the identity times anything is just that anything. Okay? And add it together, you get what you have. Somewhere there. Oh no, come on. Where am I going to put it? So you get 3x1 plus 2x2 plus s1 is supposed to be equal to 160. Can you see the 160? No. Okay? And the second row is going to be x1 plus 4x2 plus s2 is equal to 200, and that's this. Everybody all right with that now? No more questions? So if anything's unclear, just shout questions at me, okay? Otherwise you wouldn't have to be here, and you wouldn't have to be paying. You could be watching the YouTube. No, next week, yeah, no one's going to come. Okay, so you might remember we called this vector B. Okay, so that's the vector of the right-hand side. And we called this matrix A, and we call this vector X. And this is the identity matrix, and this vector is called S. All right? And so what the tableau looked like was here it said bases, so there was some bases there. Here it said val, and here we had the vector B. Okay, and here it said x, well, x transpose or something, and here we had the matrix A. Okay, and here it said S, this is the transpose, so S transpose anyway, and there was the identity matrix here. And here it said Z, or objective. Okay, what was here below B in the objective row? There's a 0 there. What was here below the identity matrix? Yeah, all zeros. And what was here? The opposite numbers of the objective coefficients. Okay. So this was, so the original LP, when you write it as matrices, was to maximize Cx. C is a vector, it's a row vector, X is a column vector. Multiply like that. And the constraints were Ax is less than or equal to B, and X is greater than or equal to 0, 1 by 1. For this, we could rewrite as Ax plus Is equals B with the slack variables, and then we want that X and S are all greater than 0. So this is with slack variables. Okay. Does that matrix notation make any sense to you? Say yes. Do you have any specific questions about it? There's nothing going on mathematically. There's absolutely no change in everything. The only change is in the notation. So instead of writing 3x1 plus 2x2, we write the matrix of all the coefficients as a matrix, and we write a vector of these decision variables. And we do the same with the slack variables over there, and so on. Okay, but it doesn't change the meaning of anything. It's just really is just a change of notation. No questions? Good. Right, so this is the end almost. Don't go yet. From here, next week, we'll start by looking at the matrix notation, really. And we'll do properly what is called LP duality and the so-called weak duality theorem. Before then, you have an exercise, like a homework exercise at the back. Okay, so I would like you to write out your solution to this by next week, Monday lecture, and then we'll see in the labs again. And I've got one assignment which is about doing something on Mosel, so I'll explain it in the lab. Revise your Mosel Express skills by Thursday. And I'll see you on Thursday.